Hi, so today we're going to look at symmetry, and we're going to start with looking at the reflective symmetry of 2D shapes. All right, so let's look at a couple of examples. All right, so the first example we have here is which of the following reflective symmetries apply to the parallelogram below. Let's examine the parallelogram in terms of reflective symmetry. Okay, well, reflective symmetry means that we have a line of symmetry, and are the two sides are the two sides of the line of symmetry, are they reflections of one another? So let's take a look first of all at the first choice here. Is this a reflective symmetry over the line segment CG? So let's create the line segment CG and let's examine that. Here's our line segment CG, and what we would expect here is we would expect each point. So let's look at obviously C and G are going to stay where they are with a reflection, right? But look at each point A, H, and B, and let's see, do they map directly across to the other side? How do they map across to the other side of the line of symmetry? Well, here we're going to make a perpendicular line from H to the line of symmetry, and we're going to bring that perpendicular line, we're going to bring it directly across. And what we should see, if this were a reflective symmetry across the line, the line CG, we should see a point H dash right in this location right here, and we do not, right? So what you would expect is you would expect A to map directly across over here. So A dash would be roughly here, let's say, and you would see B dash being roughly here, right? So that would be a reflective symmetry across across the line segment CG. So this is not a reflective symmetry across the line CG. Let's take a look at the line DH. All right, once again, let's construct the line DH, the line segment DH rather. So here's our line of symmetry. Maybe try that again. Try and get it a little bit more accurate. Here's our line of symmetry that we're being asked to examine. And what we would expect here again is we would expect that if we map a perpendicular line, right? That's the most important thing here. If we map a perpendicular line across, if we map the shortest distance, which is a perpendicular line from C to the line DH, and out the other side in the same distance, we should see the point C dash. So let's do that. Let's start first of all with the perpendicular line, and we're going to try and get it as perpendicular as we can. It's not quite, but I'm sure it's close enough. And we take that perpendicular line, we measure out the same distance on the opposite side. We would expect to see it. We would expect to see the point C dash right here is where it should be, and it is not. So we see that if this were a reflective symmetry, we should see this image would look more like a rectangle, right? Look more like a rectangle right here, rather than the parallelogram that we see. All right. So the parallelogram is not a reflection across either of these lines, the given lines. Okay, let's take a look at another example. Okay, here's a kite right here. Yeah, a kite is a shape, right? It's not just a toy that we play with, right? And we've been asked, is this a reflective symmetry over a variety of the lines that we've been given here, right? So the first one we're going to look at is y equals x, and then we're going to look at y equals negative x minus 5. So I'm going to write these up here so that we can examine them properly. So the first one is y equals x, right? And the second one is y equals negative x minus 5. So negative x minus 5. Those are the two lines that we're going to examine, right? Well, the first one, right, we've got both of them right here on the graph. Let's look at the line y equals x first of all. Okay, well, with the line y equals x, we would imagine that we should be able to take each vertex of the kite and map it directly across in a perpendicular fashion, a perpendicular line across the line y equals x, and we would see the image of that point on the other side. So take, for example, this vertex right here. If we map this vertex right here, the vertex on negative 5, 0, if we map it directly across the line y equals x, what we see is that it does indeed map directly across it, right? It's mapping right where we would expect it to be. And indeed, if we choose any point, right, any point at all on the line, on the side of the kite, right, and we go in a perpendicular line across the to the line y equals x, and then we move that to measure to the opposite side, we should see the other side right there. Okay, so we do see that the kite is a reflective symmetry across the line y equals x, so that one works for us. And as we might actually expect now, when we, after doing that, when we examine the line y equals negative x minus 5, we would expect to see being able to fold this image over, right? Being able to fold one side over on top of the other and that it would fit right on top. Well, it's quite clear that it doesn't. One is a much longer, this side is much longer than the other side. So mapping this point right here directly over, we can see that it's 1, 2, 3, that's about 3.5, and 1, 2, 3.5. So again, and a half, 1, 2, 3, and 1, 2, 3.5. So we would expect to see this shape here to be a reflective symmetry, and that is not what we've been given, right? So the first is, so the line y equals x is a line of symmetry for this shape, but the line y equals negative x minus 5 is not a line of symmetry for this shape. So there we have that, a yes and a no, right? Okay. So there we have the reflective symmetry of 2D shapes, right? Let's take a look now at the rotational symmetry of 2D shapes, right? Okay, so the rotational symmetry of 2D shapes is very similar to the idea of the reflective symmetry of 2D shapes, right? The idea being with a reflection is the image still congruent following a reflection across the line of symmetry? With rotation, it's a little bit different. The idea of rotational symmetry is that following the rotation, does the shape map onto itself? Right? So the idea that the shape actually maps onto itself, we're being asked here, in this example here, we're being asked about rotation of 40 degrees about the origin, or rotation of 200 degrees about the origin. Well, let's find out with this nonagon here, we're talking about a 9-sided shape. So we've actually got 9 parts of it, which is probably where the 40 and the 200 play in. Let us, first of all, just do that quick calculation, right? So we have a 360 degrees rotation, right? A 360 degree rotation will be itself. If we divide that by 9, we get ourselves 40, right? So any multiple of 40 is going to be a rotational symmetry around this shape. So the idea here is, if we take this as our point, our first point A, let's say this is point A, well then, point A, not point A dash. Well then a 40 degree rotation, right? A 40 degree rotation is going to map this point A to A dash, right? That's what it's going to do, right? So this is 40 degrees, and we see 40 degrees, we've got 80 degrees, we got 120 degrees, 160 degrees, 200 degrees, right? So we'd be going, there's our 200 degrees. And so right here would be our 200 degree rotation, right? Our A, well, let's call it A double dash. Okay, so that would be your 200 degree rotation around around the origin, right? And as you might imagine, because each of these rotations is mapping a vertex onto a vertex, and it's a regular nonagon, so each side is the same measure, each angle is the same measure, and therefore this nonagon would map onto itself following any rotation of a multiple of 40 degrees. And so the two options we have here, 40 degree is a multiple of 40 degrees, and 200 degrees is also a multiple of 200 degrees. And so that would work for us. Let's take a look at another example, right? The idea, once again, is rotational symmetry, right? Rotational symmetry is mapping onto itself, right? So which of the following magnitudes for rotational symmetry of the quadrilateral below about the marked point, right? So the marked point is the center of rotation, right? So interestingly, if we are to rotate this first vertex right around the center right here, okay, we're trying to find a point where we can map vertex A onto a vertex that is identical to it. Notice that these two angles are congruent, whereas the angle about vertex A is non-congruent. So we would actually have to bring this entire image around 360 degrees in order to get a rotational symmetry where the image maps onto itself, right? And so that's the only option that's going to work for us, so none of the above. Hopefully I got that there. Notice that 180 degrees would map this image somewhat like so. Somewhat like this is what we would get with 180 degrees. And so you kind of hopefully get the idea that rotating around it's got to be mapped onto itself. And we'll do one more example, right? Here's the center of an isosceles trapezoid, right? Is at the origin, right? It's a trapezoid, right? So isosceles being two sides have equal measure, right? So this side is equal measure, but these two sides do not. It's because it's a trapezoid, not a rectangle, right? So which rotational symmetries will apply to this isosceles trapezoid, right? Well, as you might imagine, we're looking for a shape. We're looking for a situation again that when you rotate this vertex around, that it maps onto itself. Well, it's not going to map onto itself over here, right? If we went 180 degrees, we'd be somewhere along these lines right here, okay? Along these lines, forgive the pun, right? Be somewhere along those lines, and that's not mapping onto itself. Because of the nature of an isosceles trapezoid, we must go around 180 degrees before we ever get to a full rotational symmetry on that also. So neither 90 nor 180 degrees will work for this. The only one that will work is a 360 degree. Okay, so I'm going to leave it at that for you, let you practice it for yourselves, and good luck with it.